cover the ventilation requirements in the updated Vermont RBES code. We've got about an hour we'll spend on this here today. I'm going to kind of jump around through some content that is broader in the subject of the code update. So get started on a couple things here and then move through some of this content for the day today. So that being said, we're going to cover the requirements for the updated code, mechanical ventilation requirements. And my computer's not behaving. This content that I am going to be sharing today is copyrighted by the International Code Council. So the ICC is the agency, standards agency that publishes the building codes. So Vermont's version of the International Energy Conservation Code is the Vermont RBES. So what we'll be sharing today is content that is available from the ICC and is copyrighted by the ICC. A fundamental outcome for me in doing any of these trainings, the code has been around for a while, but the bottom line is that we're building and maintaining durable buildings. And a lot has changed with what we build with and the expectations and outcomes we get out of buildings now than what we were building with in previous generations. So, really the fundamentals to take away of this are just being aware of what aspects of the construction we have control over and what aspects of how that building will be used over time we can attempt to control and maintain. So that's the broader context for what we're sharing. The RBES code has been in effect since 1997. It was an act by the legislature that was passed at that time to adopt the energy code as the code of record that applies to single family and two family residential construction in Vermont and multifamily as well. It is Vermont's version of the International Energy Conservation Code. And the code is typically updated on a 3-year cycle to follow the update cycle that the IECC has. And we are currently still under the 2020 Vermont RBES, which went into effect of September of 2020. And this updated code will be coming into play as of July 1st of this year. Where you can find the code information is hosted on the Vermont Department of Public Services website. So if you go to the Department of Service site and go down to the left side of the screen through the efficiency tab, you will find the content and all of the links to both the RBES and the CBES codes. And as you click into the RBES, you'll find the current code in effect. And then if you scroll down on this page, it'll also provide you access to all of the previous versions of the code itself too. So this is where all the code content lives. Specifically to the links that'll get you to the information. We have the handbook, which is kind of a summary document of the code that is available both digitally and by print. We can mail you a physical copy of that here from Efficiency Vermont if you prefer a printed version of it. The link that I have the arrow pointed to here is the link to the ICC website where the code exists, where the full code information can be found. And this is also where you can find the code certificate to complete for any relevant project and the owner builder disclosure statement, which is an alternative record keeping for compliance with the code if you are an owner builder and meeting that criteria. And this also has the link to the ResCheck software, which is ResCheck is one of the 3 compliance options available to comply with the code. And to distinguish between the code and the handbook is a document that's been published by the department in support of the energy codes for many iterations at this point. And it is kind of a guidebook and summary to the actual full code itself. The full code and the actual statute and law of the energy code is what is published by the ICC. So just to be aware that there is a distinction between these two and that the ICC code itself should be the document of record that you're using if you want to know exactly what needs to be complied with, how, and the expectations thereof. So I try to just stick to the ICC content and the references in the ICC code in the training work that I do. The updates to the code are not yet available as far as the final versions of these, as the handbook and the ICC published version of it. Those are in process still right now of being published. The handbook is still being updated at the moment. The International Code Council has the adopted final version for the 2024 RBES. It's in their queue to publish it on their website, so it's accessible, but neither is available yet. And we are anticipating that it'll probably be close to the effective date before those would be available on the department website. The updated content is available through the Department of Public Services website right now. If you look at the code update information, you can find links to and access to the what's called the red line version, which is the edited version of the 2020 code, which has all the changes and additions to it that can be found there. So those are the documents we're referencing in the content to share with you here today. Efficiency Vermont's role: we are not in any way, shape, or form code enforcement. There is no enforcement entity in the state. The intent of the code is that those of us who are in the business of residential construction would know and interpret and be able to follow the code completely and be able to comply with it. Efficiency Vermont operates the Energy Code Assistance Center. So we have a toll-free number that you can call to reach our customer support team, who can answer the majority of questions relating to the code. And then if you have further questions or want to go deeper into that, they'll put you in touch with one of the energy consultants, such as myself or a colleague. And then you can also reach out to the Department of Public Service as well if you have more deeper questions around the implementation of the code as a statute itself. Let's see if there's a question here. All right, thanks, Alex, for putting that link in there as well. All right, so I'm going to, these are the links to the updated codes, as I just mentioned. So if you want to go see the full adopted code language for the 2024 RBES, which is what it's going to be called now, is the 2024 RBES rather than the 2023, given the implementation date. So these are the links to take you to those documents. And I'm going to skip forward from here to some more specific content around mechanical ventilation. So one of the key things reasons we need to be paying attention to ventilation in our buildings is from the standpoint of protecting the fixed assets of the building, which are the building envelope. The building envelope, is the boundary between the inside and the outside, the pressure boundary between inside and outside, and the different, delineation of trying to keep a happy little microclimate for the occupants in check, no matter what's going on in the world around it. And we are at a point now where we are expecting a lot of our building thermal envelopes to both thermally protect and keep the occupants comfortable, but also to remain durable for generations to take advantage of these buildings as well. We're building with a lot different materials than we did before. We're building with different processes. So, what you're building for the building envelope and the building shell is essentially the passive control that you have to keeping those assemblies from being damaged or incurring moisture loading over time. The building envelope will load moisture regardless of how well we detail the different control layers. We do have the ability to influence in regard to thermally protecting the building and keeping air from moving through building assemblies and keeping moisture from loading into assemblies. So those are the things that we want to pay attention in detail to when defining your thermal envelope. But we also now really need to be paying attention to keeping moisture in check from within the building and the generation of moisture within the building. So, there's kind of a sweet spot of relative humidity to maintain during the heating season. And during the heating season is where we're getting moisture and vapor drive into our building assemblies. So, we can do the best we can, and we should be the best we can, doing the best we can. with keeping moisture out of assemblies and air out of assemblies, but we do have to keep relative humidity in check inside the building with some mechanical system that is going to keep moisture in check, and then also eliminate pollutants from the building and just create a good, healthy indoor air quality environment. So the key risk that we're trying to mitigate, both with our passive controls of what we put in for control layers into building assemblies, and then by way of having a well-designed and well-functioning mechanical ventilation system, is preventing condensation from occurring within building assemblies. And condensation occurs when we have moisture-laden air coming in contact with cold surfaces that are below the dew point. And when warm air with moisture in it comes in contact with those cold surfaces, it goes from a vapor to a liquid. And that's where it can accumulate. And if it's accumulating to a high potential and there's not a pathway for drying and there's nothing in place to keep that moisture loading from continuing, materials, and especially modern materials, engineered lumber, can start to break down. And that is a critical key point to be preventing through design and then through mechanical systems. So really there's a couple key takeaways from this that simplify it, is that really two control strategies to deal with this is making sure we do keep that relative humidity in that happy range within the building for the occupants and then for the building components itself. And then if you are going to be having air with moisture-laden warm air in the building coming in contact with surfaces, you want to make sure that those surfaces are not cold and below the dew point. So there is when we're talking about new construction especially, there is a tremendous amount of embodied water in these buildings, especially in the first couple of years, that needs to stabilize. Your typical concrete foundation, if you have a full basement and your average size house, there are gallons and hundreds of gallons of water embodied in that concrete that is going to take a long time to dry out and stabilize. So you have very high moisture loading, especially in those first few heating seasons as a result of that. And then just occupational use within the building creates a lot of moisture that needs to be checked. We are building very tight building envelopes at this point, because the less air movement you have through building assemblies, the less transport of moisture vapor you get in the first place. But that also means that there's not a passive way for air exchange to occur anymore. The old buildings that were not built with any intention to try to have good air tightness and even thermal insulation have a lot of air moving through them. And so, those assemblies in these older buildings can load with a lot of moisture, but there's so much air movement through the building that moisture eventually leaves those components and dries out. We no longer have that happening with modern construction. So we really do need a good mechanical system to be keeping things in check. The primary thing that we're avoiding against and mitigating against here with good vapor control inside the building, as far as a vapor control layer, and then also by good mechanical ventilation, is preventing the transport of moisture, water vapor move through air. And that is why you have different transport mechanisms for moisture that can get into assemblies. You have capillary action, where you have wicking essentially from wet to dry that can transport moisture. Vapor diffusion, you have moisture vapor that will diffuse and move just kind of through pressure differential through materials. But the bulk of water can be carried if you have air movement through assemblies. And that's why it's critical when you're detailing air barrier and vapor control layers to make them as airtight as possible. So just as a kind of a physical example of this is a pretty well-known study that was done by the Building Science Corporation many years ago, of looking at vapor diffusion through drywall into your average building assembly, insulated building assembly. So through a typical heating season, 4x8 sheet of half-inch drywall that's seeing a average temperature of 70 degrees and an average relative humidity inside the building of 40% throughout the heating season, you'll get about a third quart of water diffusing through that material during that heating season. But consequently, if you put a 1 square inch hole into that same assembly, or that same 4x8 sheet of drywall, that has the potential then to transport up to 30 quarts of water into the assembly behind it. So that is a tremendous amount of moisture loading that would be occurring into the insulation, getting to cold sheathing potentially, and just accumulating in that assembly throughout that heating season time. So that is why it's critical to have good airtight assemblies on the interior of the building, just as much as we want to see a good airtight air barrier as our pressure boundary between inside and outside. And this is the dynamic we're seeking to avoid against, where we have you have warm air with high relative humidity inside the building, diffusing and or leaking by air into a building cavity. And what we don't want to see happen is that moisture laden air come in contact with a cold surface that's below the dew point somewhere within the wall, because this cutaway of fiberglass and OSB sheathing here on the right, that white that you see kind of bonding the fiberglass to that OSB is not spray foam, that's frost. So this is the potential that can occur when you have a very poor or non-existent vapor control layer and not good or none for mechanical ventilation as well. Because this is the potential outcome we see with modern materials and modern assemblies. So these sorts of, potential for damage, this can occur over a relatively short amount of time, 10 years, 15 years, sometimes even less if it's really bad. And then this is a very expensive failure to be repairing and fixing in the end. So this is the reality of what can happen if we're not paying attention to critical details of air tightness and vapor control layers inside the building, good air barriers as far as pressure boundaries between inside and outside, and then a good mechanical ventilation system. So bottom line fundamentals here is just keep the water out of the assemblies in the first place with good control layers. If there is going to be moisture loading into assemblies, which inevitably there will be, we're mitigating as much as we can passively with what we detail into these assemblies, but just there will be some moisture that does accumulate in assemblies during the heating season. So that is why it's critical. There needs to be some pathway for those assemblies to be able to dry out if and when that does occur. And that's where we get, perm ratings for different materials to be considerate of. And then if a material is going to see moisture, make sure that it's above the dew point. It's not going to hit a cold surface within the wall and start to accumulate. So on the vapor control side of things, we have materials now that are vapor control layers, vapor retarders that have the ability to be as close to being vapor closed as possible during the heating season. When the conditions inside the building are in effect low relative humidity compared to where they could be. So we're talking relative humidity inside the building being stabilized at between 30 and 40% relative humidity, trying not to go above that or below that. And in those conditions, these sorts of intelligent vapor retarders will be pretty much vapor closed to prevent moisture vapor from being driven into the assembly behind it. But then during this time of the year, when we have warmer weather, there's not a real pressure differential between inside and outside. And just generally, we're seeing, what the outdoor environment is for humidity of higher humidity levels, 60-ish, 70%, depending on the day. These materials will open up and allow for any moisture that has accumulated in the assembly behind it to diffuse out and dry inside the building, inward to the building. So it's kind of a valve that allows for drawing potential back into the building during the summer months and prevents moisture loading during the heating season. And this is just an example of some of the products that are available on the market. The lower the perm rating, the more vapor closed the material is, the less moisture vapor it will allow into the assembly. And these are the values that we're seeing here to look at for the heating season. And then the higher permeability is when that material opens up this time of year, when you have the higher relative humidity it's seeing and the ability for that assembly to dry out. So these are passive control layers. The details are really what matter here, making sure that materials are installed consistently, made airtight, because you are stitching together multiple pieces of material to create an assembly and a whole. So really looking at your perimeter of the space that you're detailing, making sure that the vapor control layer is glued at your top stud, your corner stud, your bottom plate, and any window and door rough opening is also sealed up as well. So these are, again, just some of the details that need to be accounted for on the passive side of things before we get into the mechanical side of things for ventilation. Window rough openings need to be considered as well from a vapor standpoint and not just an air leakage standpoint. The typical window sealing foam that you're going to use to seal up the gap between the window unit and the rough opening is an open cell foam that will allow moisture vapor to move through it. So considering that and what we can do to keep moisture vapor from getting into that crack around those assemblies needs to be accounted for at this stage too. So that was all kind of the lead into the actual mechanical ventilation requirements, because I do think it's important to take that into context that, you know, there is passive control that we want to maintain for loading building assemblies with moisture. But when it comes down to it, the mechanical system that's actually going to be operating and keeping things in check is a critical component, so that those passive parts of the building can not be stressed and to be able to perform as effectively as possible. So in the way that the energy code is laid out, there are 5 chapters in the code. Chapter 3, general requirements, is where you're going to find most of the information about the mechanical ventilation requirements in the RBES, and specifically section R304. So again, this is from the ICC document that I'm sharing here. Not sure if you're seeing my screen or not here, or what you're seeing of it, but hopefully I'm not hiding text with my picture here. Big change for the 2024 RBES is that up until now, exhaust-only ventilation was allowed in the code, meaning that you could provide the minimum requirements for mechanical ventilation, whole house ventilation in RBES by using a bath fans that were controlled to be able to run automatically throughout the day. So exhaust-only systems have been essentially the baseline allowable to this point. The change for 2024 as of July 1st is that every home built to meet the new updated code will need to have a whole house balanced ventilation system installed. So exhaust only is no longer going to be allowed. We're going to be looking at balanced heat recovery ventilation equipment as the mandatory standard at this point moving forward. Quite honestly, this is something that's catching up to what we're already seeing as need for new buildings. You know, the air tightness of the building envelope and just the materials involved in the assemblies, as I've been talking about here, have really kind of already yielded us in the direction of needing a good balanced mechanical ventilation system rather than just exhaust only. So this is something that, you know, has been around for a while. There are many systems installed, and what hopefully we can look at here are just the fundamentals about how to get a good system installed beyond just the piece of equipment that can do the heat recovery and the ventilation piece. So there is a minimum performance requirement and called out in the code of equipment that has a minimum sensible recovery efficiency of 70%. This has changed, so I apologize for that number being off here. So a minimum performance requirement is 70%. That's sensible recovery efficiency. That's essentially how effective the heat recovery core is at extracting BTUs and heat energy from the exhaust stream and putting those into the incoming fresh air stream of the system. And then a minimum fan efficacy of a fan efficiency, essentially, of 1.2 CFM delivered through the system per watt of electricity consumed to move the air. There are basis of design for sizing mechanical equipment and how much ventilation air is required specific to the building that's being built. Just like you would be doing a design load calculation for a heating system or a cooling system, and specifically designing to that building's need for what type of mechanical heating or cooling system is required. The ASHRAE 622 standard exists as the standard of the industry standard of design for minimum ventilation rates for single family construction. Passive House, the Passive House Institute also has ventilation standards that they have developed, which are considered equivalent to the ASHRAE approach to model your CFM needs. But the ASHRAE approach has been pretty much kind of the common method to use in our market.
Don't mean to interrupt, Pat. So looks like we've got a couple of questions here rolling in. Do you want to answer those now or
Sure.
a little later? Awesome. So Jim asked, when you're talking about the balanced ventilation, does this exclude the Lunos type system?
So the only thing that's written into the code as far as minimum performance requirement is this 70% sensible recovery efficiency and the 1.2 CFM per watt fan efficacy requirement. So that is the minimum basis to be met. The 1.2 CFM per watt of fan efficacy / efficiency is pretty much aligns with ECM motor equipment. So that's kind of one of the things that stands out as far as a differentiation between all the different products that are available on the market. So the Lunos product, if it's meeting those minimum performance requirements, would be considered allowable. The difference between the Lunos systems is that they are not a distributed system throughout the building, so it's not a unit connected to ductwork. It's paired through wall ventilators. So as long as they're meeting that performance requirement, they would be considered allowable under what's been written in the code. And then Bruce, your question was what temperature and fan speed is the 70% SRE required? I think I have a slide that'll show that here in a moment, but it's at 32-degree outdoor temperature. And then it hasn't been clarified to a full extent, but the sensible recovery efficiency is seemingly meant at max capacity of the equipment. And I'll show you that here in a moment in the slides around the HVI directory and how to find that information. Okay, thank you. So we're talking about a whole house ventilation system with the intent being here that you have ventilation air moving throughout the building. And then in conjunction with that, there is minimum performance requirements for local ventilation. And what local ventilation means, point load moisture sources, rooms in the building, bathrooms that have showers, baths, etc. Those rooms, those bathrooms need to have a minimum capacity of at least 50 CFM of ventilation air if the whole house system is going to be run intermittently, meaning it's coming on for say 20 minutes per hour or 30 minutes per hour on a timed basis, something like that. When it comes on, it needs to be moving a minimum of 50 CFM. Or if it's going to be a continuously run system, a system running at a low volume throughout the day, 24/7, then it needs to meet a minimum of 20 CFM in those spaces. So the equipment can be either heat recovery or energy recovery equipment. The difference between the two is that an HRV is only going to be recovering the sensible heat. It's not going to be recovering any of the moisture in the air, any humidity. Energy recovery equipment will be recovering a portion of the humidity in the air that is being extracted on the exhaust side and returning that into the fresh air side of the system to be moved throughout the house. So there's not a requirement for one versus the other. There's been a lot of conversation about what's appropriate in our climate. I think a lot of ERVs are being installed, perhaps more than HRVs, because it's important to keep relative humidity in check and not have elevated relative humidity throughout the heating season. But it also is critical that we don't have consistent relative humidity that's really low and can create discomfort for the occupants. It can start to affect building materials and the building starting to, shrink and shift and move in ways we don't want them to be moved. So there's some consideration there between HRV or ERV as you're looking at equipment. So the minimum performance requirement again here, this should be 70. That's a change that was recently discovered in the code content. So 70% SRE at 32-degree outdoor temperature to the question that was raised a moment ago. It is something to be very much considerate of when looking at equipment as to its capacity and ability to be able to still work when it's below 32 degrees outdoor temperature. So I'm going to show you some information here in a few minutes about how to find equipment that is actually specifically rated and tested at low outdoor ambient temperatures, because that is the critical time for when we really need these systems to be performing, is in those cold months of the year. So there's definitely a distinction in equipment that is available in the market for what's cold climate rated and tested versus, equipment that is not. So the fan efficacy side of the equation is something that you would have to look into beyond usually what's provided by submittal data from manufacturers. The CFM per watt is basically dividing the amount of CFM delivered and the amount of energy, electricity run to run the motor to deliver that CFM at 32 degrees. Those data points can be found through the Home Ventilation Institute, which is basically a certificate or registry of ventilation equipment that manufacturers will provide to HVI testing data of their equipment at different testing points and data points to then be listed in that registry. So that's an important tool to be aware of if you're not already. So look at the HVI site and look through their certified directory for balanced ventilation equipment. And this is where you can find all the performance data around sensible recovery efficiency at different temperatures, flows at different static pressures in the duct system, and information such as the CFM per watt delivered. So the reason we're getting to this point is, the idea of going from exhaust only to balanced is when you have exhaust only fans in the building, you're hoping and relying on air leakage through the building assemblies to be making up your fresh air intake, essentially. And we are not at that point anymore. If you're building a code compliant house at this point, the ACH numbers that are required to be met really are eliminating most of any passive air leakage through the building envelope. So if you do have exhaust only fans working in a tight house, you're often depressurizing the building, and you're really not getting good, effective fresh air intake into the building. And you're also really not circulating air and moving air around the building. In the current code up until July 1st, you could prescriptively meet the whole house mechanical ventilation requirement by putting one bath fan that's rated to move 100 CFM in one bathroom of a 3,000 square foot house, with 4 occupants, that's on a timer to come on and run during the day and be considered that you have a whole house ventilation system. But practically speaking, that one bath fan is not going to be providing ventilation air throughout the building. So this is what I was getting at earlier when I said we're just kind of at a point where this is, whole house distributed ventilation has been more of a necessity for a while now. And we're now getting to the point where this is what the expectation is to be met. So with a balanced system, you are providing equivalent fresh air directly from the outside into the home, moving through the HRV or ERV, where the exhaust stream of air that's pulling moisture-laden air and pollutant-laden air out of the house through the same piece of equipment, and those two air streams cross paths in the heat exchanger, and that's where the BTUs and or humidity is exchanged into the incoming stream of fresh air. So you're getting conditioned air into the building. Different equipment available on the market has different filter options as well. So different MERV rated filters and even up to HEPA filtration as well. So you can be filtering out dusts and pollens and other pollutants into the building as well. And in balance, meaning that the exhaust side of the system and the fresh air side of the system are to be balanced within about 10 to 15% of each other for flows. So you're not creating negative pressure differentials in the house through exhaust only systems or through suction. You're keeping a neutral pressure plane within the building with a good effective ventilation system installed. Looks like we may have another chat. Oh, Alex, you put the HVI directory into the chat. So thank you, Alex. That's great.
Yeah, I will say that I don't think that was the exact link you referenced a couple slides ago, but it's just a
He'll get you to there, though.
Okay,
Yeah. Thank you.
Mhm.
So to this point, we've been talking about HRV or ERV equipment. And we're essentially just talking about a pretty simple box that has a fan motor in it and fan, and a heat exchange core and 4 ports that come off it typically to bring in an exhaust air and then move it throughout the building. What is just as critical and almost even more critical to the performance of that piece of equipment to be useful for the building and for the occupants is that it's connected to a well-designed and well-functioning duct system. So this is critical to the success of the system, and it's critical that this is something that's thought out and designed into the building from initial design and concept stage. It's not something to be thought of after the fact or just kind of fit into the building once the structure is built. Really, you need to be understanding where is the equipment going to go, what duct sizes do you need to move air effectively to the different rooms it needs to get to, where do those ducts need to go, what framing considerations need to be made to allow for that. So really, these things need to be accounted for at design stage. And in an ideal world, those things would be identified on the plans. You know, if it's not going to be showing up on the plans drawn up by an architect or designer, then whomever is going to be installing the system should be able to have a chance to look at those drawings and to identify where the equipment's going to need to be, because that may have changes required on structure or other considerations to be made, because you don't want to have a 5-ply microlam right between where the ERV needs to go and the main plenum line, trunk line coming out of that needs to go, with that right in the way. So good design is critical here. We're not just talking about fitting it into the building, but good duct design and following good duct design principles for pressure. You want to be able to get the effective delivered CFMs into the individual rooms in the building. And that comes down to, the practical guidelines around duct design, and designing from the room back to the unit, essentially, for how you want to be specifying your terminals, your fittings, your transitions, etc., so that you're getting effective flows from the unit. Because this is an outcome you don't want to see. And this is still, happening and not uncommon to come across, where this is a common one I've seen a lot, where you see an HRV or an ERV in the attic of a new build, and the only access to that piece of equipment is through a 16-inch square hatch in the bedroom closet that you have to take the shelving out to get to. ERVs, the HRVs have cores in them, those heat recovery cores and filters that need to be cleaned and maintained a couple times a year in order for them to work. So they need to be accessible, and they need to be aware, the homeowner needs to be aware that they need to be maintained. This is another example where this is a closet, and this is a closet header here, and there's the cabinet door of the ERV that needs to be opened. And these are both one and done ventilation systems here, where they will run until that filter needs to be cleaned and maintained. And then once it gets to that point, since there's no way to access that filter, you no longer have a ventilation system running in the building. And that's not the outcome you want as a builder or general contractor to have. Your expectation being that there's going to be an active ventilation system running in this house that's going to keep everything in check and everything happy, and then have that system shut down that you're not aware of, and then things can start to spiral on the backside of that. So another critical piece of this, as I was saying a moment ago, when it comes to the duct design, you really want a ventilation system to be operating in the background, that the occupants are not even aware that it's there doing what it's doing. Meaning that you want a piece of equipment and a system that is operating quietly so that they don't hear it, and that also you're getting good and effective, sensible recovery, heat recovery, so that you're not moving cold air into the rooms and onto the occupants. Designing the system, you should be considering equipment that can meet that CFM requirement through the ASHRAE design that I'll show you more detail on here in a moment. But the equipment should be sized to meet that minimum flow rate for the building within the middle to moderate range of capacity of the ERV or HRV. And what we should be looking at here is either multi-speed or more ideally variable speed equipment, so that you can dial the equipment in to be running at a low to middle speed to move the amount of ventilation air required to the house. Because the higher the fan speed and the more air moving through the ductwork, the noisier the ducts will be, the noisier the system will be. You'll also be minimizing your sensible recovery efficiency through the heat core, because you're moving more air across it than it wants to see. You have higher energy penalties there. So trying to consider, design within the middle range of the capacity of the equipment is critical. A lot of different options of equipment on the market. Most systems are intended to be connected with site-built duct systems and rigid ductwork and/or flexible ductwork off the unit itself and move throughout the building. There are some manufacturers, Zender specifically, which is a European manufacturer that has a manifold and home run system essentially from their units, where you have small diameter flexible duct that goes throughout the building to each individual room, and each of those ducts comes back directly to a manifold from the piece of equipment itself. So you have a lot of flexibility in that unit to be able to dial in your flows room by room. But if you are doing a site-built rigid pipe duct system connected to the ERV or HRV, you really should be designing into that dampers and terminals that you can allow and adjust for flows, because you want to be able to dial this piece of equipment in and the system in once it is installed. The code does allow for the integration of HRVs or ERVs into a forced air heating system and shared ductwork. My opinion, ideally, there would be two separate duct systems if you are in that situation. One, your heating and cooling system is its own thing, and the ventilation system has its own duct system connected directly to the HRV or ERV. The reason I say this is because just equipment wise, we're talking about two entirely different needs for the duct design, where the ARV or HRV is moving less air at a lower volume and different static pressures through different duct diameters, whereas a forced air heating and cooling system is moving air in a different manner. If you are going to be combining the equipment, which is not an uncommon scenario, then you do need to be accounting for the fact that you're going to be relying on the air handler and the motor and the blower of the heating system furnace, essentially, to be moving your ventilation air more so than you are the blower and motor of the ERV or HRV itself. So you have to set up these systems with those pressure differentials taken into account, and the ability to be able to control the ventilation side of the equation through the air handler of the furnace, so that you're getting ventilation air when the furnace is not coming on when it's a call for heat or cooling. The code also does require that if you are going to do this sort of combined duct system, that the air handler motor itself for the furnace is an ECM motor. When we're talking about retrofit applications, there are quite a few products in the market that are designed around retrofit, meaning that they are small cabinet assemblies that can be fit into existing framing cavities and utilize smaller diameter ductwork. So you have a little bit more flexibility of running the ducts to these systems and getting these systems installed in existing cavities where you're not specifically designing around the needs of the duct system and or the equipment to fit into the building. So a lot of options for equipment on the market, another noted. But how do we get to the point of knowing what to design for? So this is the ASHRAE 622 standard for defining ventilation rates for residential construction. There is a tool available online called the RedCalc tool. And this is just a web-based tool that you can go to and enter in your data points for the building that you're building. And this tool will do the ASHRAE calculations for you, and then give you what your required ventilation rate is needed to be for that specific building. So in using this tool, you're defining the type of construction it is, specifically what climate it's built in, because that has an impact on the ventilation needs. Size of the building, number of occupants, exposure. If you are doing blower door testing and you're using blower door numbers and or estimated numbers, you can account for that into the inputs here too. That would be considered the infiltration credit. So we'll talk about that here in a moment. But a very handy tool to use that's readily accessible, that gets you to the outcome of what you actually need specifically to the building that you're building for ventilation air. So we'll walk through this as an example. So the example that we'll use to show you how this tool works and how to get to the idea of designing the whole system is talking about a 2,000 square foot house, 3 bedrooms, 2 stories plus a basement, 4 occupants in the house, 2.5 baths, kitchen, and blower door testing done on the building that with a result of 600 CFM at 50 pascals of air tightness. So that's the amount of air moving through the building envelope from an air leakage standpoint. So we'll use the ASHRAE RedCalc tool to do our calculations here for this specific building. So it's a new construction. This tab right here that says use infiltration credit, what we're doing there is the blower door test and the amount of natural air leakage through the building envelope can be used as a consideration for the amount of ventilation air mechanically needing to be delivered throughout the house, meaning that it's accounting for the fact that there is X percent of air leakage through the building envelope, and that can be technically accounted for as a part of your ventilation needs for the building. So I'll show you how that sugars out here in a second. But you're entering in the location the building was built in. And then this Montpelier point here is you're actually using a local weather data point to go into the calculation. So you're going to be specifically trying to find a weather data point here that's local or near where the house was built, putting in the square footage, occupants, the exposure of the building, the height of the building. And then in this scenario, like we said, we do have a measured CFM number that would be entered. So enter in those data points and basically have it calculate. And then the outcome you're getting here are a few different data points. The infiltration rate is essentially 27 CFM of natural air leakage through the building annually. A total required ventilation rate of 90 CFM for the building. And then taking into account that the house is going to have that volume of CFM moving through the building shell throughout the season, this is giving you an equivalent required mechanical ventilation rate to make up that difference of 63 CFM. So the building needs 90 CFM total. This is allowing for the fact that because of the CFM number, the building is going to leak an average of 27 CFM relative to the building on its own, which then means you're making up with needed 63 CFM of mechanical ventilation. So what that means is that, as again, this is a balanced system, you're going to be looking for equipment that's going to be providing 63 CFM of both supply and exhaust. So it's just an equalized volume of air on both sides of the equation moving through the building. So in order to meet the local ventilation requirement in the code, you need to have that 20 CFM if you're going to run the system continuously coming from each of the bathrooms. And in this scenario, we have 2.5 baths. And then for supply side of the equation, best practice is considered to removing 15 to 20 CFM of supply air to each of the bedrooms and primary living space. So taking that into account of what the actual needs are of the house based on the number of bedrooms, occupants, and the bathrooms, we need to be considering that against that defined 63 CFM that came from the ASHRAE calculation. This is just referencing again those minimum requirements for the bathrooms. So if you only had a system set up to run and provide 63 CFM, you'd still be coming short in the bathrooms. And in this scenario, calling out that one option would be to put an exhaust fan in the bathroom to make up for that local ventilation requirement. but that's not a good practice, and we don't want to be going down that road. And you also, would not be having enough air to move if you wanted to get to that same sort of 20 CFM average room by room for supply air throughout the building as well, too. So taking that into account, we're looking at, dividing up our numbers with what's currently here. And then this is how this would leave you with your supply side of the equation. So we're coming up short a little bit here for what you'd want to see through the different rooms in the house. Sorry, I have to keep moving my picture here so that we can see the screen. So in balancing this all out to get to an actual outcome to install in the building, we're actually moving more towards that total 90 CFM requirement for the building, not taking into account the infiltration credit. So breaking that down between the exhaust and the supply side, from a design standpoint here, we're looking at providing 30 CFM of exhaust from the kitchen. When you're exhausting from a kitchen space with a balanced ventilation system, you're not using the ERV or HRV as a range hood. You still should consider having a range hood anyway that's exhausted directly to the outside. But that port for exhaust from the kitchen would be somewhere within the kitchen area, but not intended to be capturing that sort of grease and laden air coming from cooking. So in this example again here, we're looking at breaking down our 90 CFM of exhaust throughout the building as 30 CFM coming from the kitchen, 2 full bathrooms getting 24 CFM of exhaust, and then the half bathroom of 12 CFM. So that all balances out to 90 CFM on the exhaust side. On the fresh air side, putting 20 CFM into each of the 3 bedrooms, 30 into the living room, and then again, that getting us to an equivalent 90 CFM for supply side. So this is a way of looking at designing for the whole system, balancing it out from exhaust to supply, and getting again to an equivalency that aligns with what the ASHRAE calculation gave us for total building ventilation needs. Just taking a look in the questions here for a moment.
Yeah, we got a couple up top above. Couple.
Sure.
We had one from Tom about, does RBES require fresh air supply to all spaces in bedrooms or common living areas?
So it's not calling it out specifically in the code language that a minimum amount of supply is brought to which specific places in the home, but best practice and standard for design is what I've been talking about here to this point of an average of 20 CFM to the bedrooms, the primary bedrooms that'll be lived in, and to the living spaces of the house. And again, in that example we just showed, there's some flexibility within that as you're trying to, equalize and balance out your supply and exhaust side. Requirements for additions. So depending on the size of the addition, it would come into play. Smaller additions, under a certain square footage, I'd have to look it up. It's not required. But over a certain square footage, it would be required. And for the addition only, it doesn't require that you're changing the dynamic of the existing house. But if you are doing a substantial addition to a home and a major, rehab, gut renovation sort of thing, really practically speaking, you should be considering that ventilation requirement of the whole building as a whole and how it's going to operate as a whole once complete. Bill here, throwing out Bill Chidsey, a great partner with us here in the EEN. Bill has done some really great work and some trainings and content on duct design. So there are duct principles to be considered and followed, again, as I've been talking about here. There's some resources available from what Bill has created, and then also through ACCEA. They have standards, these standards for duct design that can be followed. Ecobee thermostats can control and maintain ventilation rates with ducted heat pumps. That's a way to do the controls on the integrated system that Bill's talking about here, where you're integrating your ventilation air with a ducted heating or cooling system. And then it looks like we had some other question about credits. So, all right, thank you. So to close us out here, as I was talking about at the beginning of this section, there's a lot of equipment available on the market, and not all of it is designed the same. You know, there are different climate needs and different ventilation needs in other parts of in one part of the country versus another. So we do not have the same needs from our equipment here in Vermont that we do in Arizona or Texas or another part of the country that does not have the same climate related issues that we do. So that being said, and as I said, we want to have equipment that's working when it's cold outside. Canada does have an Energy Star ERV ventilation program, and they have a standard then for testing ventilation equipment at cold ambient outdoor temperatures. So if a manufacturer is going to list a qualifying product on the Canadian Energy Star qualifying products list, which in Canada is eligible for a product rebate, that does not exist here in the United States. There's not an Energy Star standard for ventilation equipment, balanced ventilation equipment here in the US at this point. But in Canada there is, and if manufacturers want to have that product available to be eligible for the rebate, they have to show performance testing data to Canadian Energy Star standard to be met at their performance metrics. So these requirements here are showing the SRE of the equipment at -13 outdoor temperature and at 0 degree outdoor temperature as well. Whereas in HVI, you can see that data if it's available from the manufacturer. And what the Vermont RBES is calling out specifically is SRE at 32 degrees. But the Canadian standard here is, again, requiring manufacturers to prove that the equipment is working below 32 degrees and all the way down to -13 if they have tested it at that outdoor ambient temperature. So this is also giving you CFM per watt at the different SREs and at the 32 degree outdoor temperature. So this Canadian listing is a valuable tool to consider looking for equipment from when you're talking about specifying your options for ERVs or HRVs in a new build. One of the other key things that comes out of the Canadian requirements for the listing is that there is a defined and effective defrost strategy for the heat exchanger, because once you're pulling cold air into that core needs to, if it's going to get frozen or frosted up, it needs to find, and there needs to be a functional way for that core to defrost or warm back up. So depending on the manufacturer, they may have a active electric resistance coil in there that preheats the air going into the core below a certain outdoor temperature, or you'll have systems that will recirculate the exhaust air through the core to defrost it if it does get to that point. So there's different strategies manufacturers use to keep the core working and functional when it's really cold outside. So this is sorry. Again, this is just a screenshot from the Canadian listing. So in that Canadian listing, you can actually search for different criteria. So you can put in what your SRE range is you're seeking and at what temperature it's tested at. So it's an effective tool to dig into to start specifying equipment. This is the link to access this tool and the database and the qualifying products from the Canadian listing. Again, this is recent information found that brings us again to update what's going to be in the code for July 1st. It's 70% SRE is going to be the minimum criteria, not 75. So to sum this all up, what is required here is a automatically operated system that's going to be running, again, either full-time 24/7 continuously or intermittently. That's one other thing I didn't show in detail in that REDCalc tool that the REDCalc tool can calculate for is runtime. So you can put in parameters there for runtime if you do not want the system, or you're choosing not to have the system run continuously. You can define if it's only going to run for X number of minutes per hour, what CFM would be required, and how much that runtime needs to be. So that's another way to utilize that tool. So the key takeaway here too, though, is that this needs to be designed as a system. You know, the The ERV or the HRV is just a fancy box in and of itself. You really need to have a well-designed and well-functional duct system that has the ability to be able to adjust it attached to that piece of equipment. Commissioning of ventilation equipment is not a mandatory requirement in the upcoming RBES. It is a way that you can earn points if you're doing prescriptive compliance with the code, meaning that, you know, unless you are actually doing performance testing on the system as it's running and after it's installed, you're really only guessing if you're getting the CFMs to the individual rooms in the building that you've designed for. So commissioning means that you're bringing in a flow meter and you're actually putting a flow meter up on each of the ports for supply and exhaust throughout the house and getting a CFM reading for what's actually being delivered. And then ideally having some sort of control there at that terminal to be able to adjust the CFM coming out of that terminal into the room if you're not already at your target CFM. So systems thinking, that's what really matters here. Efficiency of Vermont will continue to do more work on this side of things. We've got other ventilation trainings that have been developed and we have information on. We have some one-pager guidance documents available as well. But we're here to just answer questions as they come up as you work through these projects moving forward. So feel free to reach out to us, here to help. And if you want to reach me directly, here's my contact info. So happy to stick around to answer some more questions if there are some. But appreciate you all joining us here for past hour this morning.
Yeah, thank you, Spence. That was fantastic. If anyone would like to, you could raise your hand and we can take you off mute if you'd like to ask a question verbally. If not, feel free to drop it in the chat. We got one hand here. Okay, Bill, you can unmute.
I'd like to comment that a very cost-effective way to get more capacity out of your duct system is to oversize the ducts and the hoods that connect the unit to the outdoors. So you might have a unit that has a 6-inch port on it for the fresh air and a 6-inch port for stale air. And if you increase that duct size to say 8-inch and buy nice, generous 10-inch outdoor hoods with, of course, the screens to keep out the critters, that system will give you much more capacity when you run into compromises on your interior duct. Remember, the static pressure is measured all the way from the outside hood through the unit to the supply diffuser. Thank you.
Okay. Thank you, Bill. Yeah, the taking principles of design into account when specifying how your duct system is going to go together is critical, and really following those standards of practice that are defined by ACA to be able to get you the right components together to make this thing effective throughout the building.
I'm not seeing anything else at the moment.
All right.
Give it a minute or two, but we